For today's pre-lecture video, I wanted to look at the calculation of moment of inertia when our mass is extended over a line or an area or a volume. I wanted to do it because I'm pretty sure we won't have time to look at it in class. I wouldn't expect you to have to replicate these calculations, but I would like you to understand them conceptually. So first of all, let's talk about moment of inertia, just a quick review. So basically, what we find is when we're looking at the kinetic energy of an object that's rotating, we come up with an expression that we call the moment of inertia. I like to think of it as the rotational equivalent to inertia that we were introduced to in chapter 4 when we learned about Newton's laws of motion. Remember that the way that we quantify inertia, an object's resistance to its change in linear motion, is by the mass. So the moment of inertia, like I said, is the rotational equivalent. So it's the measure of an object's resistance to a change in its rotational motion. Now, instead of just being equated to the mass of the object, it's dependent on how that mass is distributed relative to the axis of rotation. So we came up with this expression for the moment of inertia as the sum of the mass times its radius, that's the distance from the axis of rotation, but that radius squared. The sort of shorthand that we use in physics is we say that the moment of inertia is the sum of the mr squares. The r allows us to sort of talk about where the mass is relative to the axis of rotation. Squaring it allows or disallows the fact that masses on either side of an axis would cancel each other out. So here we have the expression that we use to calculate the moment of inertia. This expression is pretty easy if we have to find the moment of inertia of several distinct masses located at very particular locations away from the axis of rotation. For instance, if we have an axis like this, here's our axis, and I have a mass here, mass 1, and then a mass here, mass 2, it would be pretty easy to calculate the moment of inertia of these two masses because I know their mass, I know exactly where they're located, and I can just do the summation. But what do we do if the mass is distributed over a large area or along a line? Is it a rod or along a volume? How do we calculate the moment of inertia? Obviously, there's a way to do this because we've already seen these expressions for moments of inertia of extended objects like a cylinder, a rod with the axis through its center or about the end, a hoop, etc. So the way that these expressions are arrived at is actually through a calculation. It just isn't that someone made them up. So we need to figure out exactly how that calculation could be done. So we can sort of start off with a picture. So again, here's our axis. And let's just think of some irregular mass because we want to sort of think of it in a very general sense. And we have the definition of the moment of inertia as the sum of the m sub I, r sub I squared, the sum of the mr squares. You know, at first we could sort of take this little piece of mass and here's its distance, but maybe we'll call this, instead of m sub I, we'll call it delta m sub I because it's just a little piece of the total object. And so this expression might change to delta m sub I r sub I squared. Well, now when I broke up and took this little piece of this object, I made it a little square or a cube. But of course we know that using these little blocks will introduce some error. This is just really an approximation. we can't really divide up this object that has nice curved outer edges into little squares. So that's not going to really work. In order to improve our sort of accuracy, we would have to let those delta m sub i's be infinitesimally small. And hopefully you see where we're going with this. We would change from a summation to an integral. So the way that we talk about calculating the moment of inertia for an extended object, instead of a summation process, it's an integration. And there's sort of two separate issues that we have to work out in this process. Of course, the radius is something that's going to change. Because as we integrate, we're going to be looking at pieces of mass that are different distances away from the axis. And then the other question is, how do we express the dm? In terms of the mathematics, we need everything to be expressed in a common variable. For instance, when I look at this expression for dm, if I just left it the way it is, the differential dm implies that we're integrating over mass. However, I've already said that the r changes as we move from little infinitesimal piece of mass to another. So we couldn't integrate it as it stands because we actually would technically have two different variables that we're trying to work with. As we sort of figure out how we can write dm, it starts to lead us into a way of expressing everything in this expression in terms of a common variable. Let's take a little bit more closer look at dm. First of all, how we're going to express that dm is going to depend on what our mass distribution looks like. What's the shape of it? Is it along a line? A linear distribution? So if it's a linear distribution, it's pretty common that we use the term lambda to describe how the mass is distributed over the length. Now, so it says that lambda would be equal to the total mass over the total length. But we could also write that as if I take a little piece of it, if I take a little piece, dl, I've also taken a little piece of mass, dm, so I can also write this expression as dm over dl. And so I can rearrange this, and dm could be written as lambda, which is presumably a constant, times dl. Although I should say that sometimes these mass distribution terms could vary, for instance in the case where maybe there's more mass towards the end of the rod. But that's a little bit beyond what we want to think about. Similarly, if I have an area that our mass is distributed over, I commonly use the letter sigma to designate the area over, the mass over the area, or dm over dA, because if I take a little piece of this, it's a little piece of area, but it's also representative of a piece of mass. So we could rearrange this to write dm in terms of dA. Finally, if we have things over a volume, like maybe a cube, when I take a little piece of the mass, so that's going to be dm, but it's also a little piece of volume. The term that I usually use to represent mass per unit volume is the Greek letter rho, which can be written as dm over dv, and we can rearrange this to write rho dv. So these are some of the ways that we can simplify the expression for dm that gets us closer to a place where we can do the integration. As an example, I want to do a really simple example that we would normally see in our book, and that is finding the moment of inertia of a uniform rod with a length L and a total mass m. And the axis of rotation is going to go down through the center of the rod. So I start with my definition of moment of inertia. Now, I see that lambda is mass over length, but remember it's also dm over dl, so I can rewrite dm as lambda dl. Now, notice that when I took a little piece of the rod, the dl, or the length of it, is actually written dx, and the distance, which is the radius from the axis to where that's located, is measured in the x direction. The variable is x. So what I see that in my expression, r squared actually can be expressed as x squared, and dm can be expressed as lambda dl, which goes to lambda dx. So this is what I'm talking about. When we substitute then these values in to our expression for moment of inertia, we get x squared lambda dx. Now see, everything is in terms of the variable x, which makes things a lot easier. And notice that if the entire rod is L units long, we start at minus L over 2, and we go to L over 2. So those are our limits of integration. So let's just try to simplify this a little bit. I can take lambda outside. I'm just integrating lambda dx from minus L over 2 to L over 2. The integral of x squared dx is x cubed over 3, evaluated at minus L over 2 to L over 2. And again, just to simplify a little bit, I'm going to take the 3 outside. And when I put in my limits, I'm going to get L cubed over 8 minus L cubed over 8, which is going to give us 2L cubed over 8, which can simplify to lambda over 12 times L cubed. Now this might not look like some of the expressions we saw in the tables, but remember, lambda can be expressed as the total mass over the total length. So where we had I is lambda over 12 L cubed, we can substitute this by m over L times L cubed, and we end up with 1/12 L squared. And if you compare to some of the tables that you see in your book, you'll see that this is exactly the expression that they have for the moment of inertia of a rod of mass m, length L, where the axis of rotation goes through the center of the rod. And so that's just a simple example of how we can use that expression to find the moment of inertia of an extended mass.